Hello viewers, welcome to this next lecture on the NPTEL MOOC course on mathematical portfolio theory. In the previous lecture, we started off with a new topic on optimal portfolio and consumption, and we mentioned that we will look at the optimal portfolio as well as the consumption in both discrete and continuous time model. And we started off by talking about a market model and consumption as well as utility functions. And the approach that we will take for discrete time portfolio optimization is going to be what is known as dynamic programming due to Richard Bellman. So, we continue our discussion in the discrete time framework for this problem of portfolio optimization and begin today's lecture. So, we pick up from where we left last time, that is utility functions in multi-period setup for discrete model. Okay, so we begin with the supposition that the investor cares about the consumption process as well as the final wealth level. So, that means that the investor cares about the ongoing consumption process in addition to, of course, what is going to be the terminal or final wealth at the end of the investment period. So, accordingly, let us be very specific now about this consumption process and the final wealth. So, we let C of t denote the amount of money that is consumed at time small t, and let x of t denote the wealth level at time small t. Further, so since we are talking about final wealth, so obviously we have to consider an investment period. So, further let the investments time window be 0 t. So, that means an initial investment is made at time 0 and it is terminated at time capital T. So, then the objective is the maximization of the following. So, earlier what we had, so suppose that we take two utility functions u1 and u2, u1 for consumption and u2 for final wealth. So, an investor can have different utilities, one for final wealth and one for consumption. Of course, they can be identical also, but we are just looking at the generalized setup. So, then in the original framework what did we have? So, the utility of the final wealth will be given by u2 of x t, and the utility of the consumption is going to be given by u1 of c t. Now, this u1 of c t, this happens at different times. So, these are values obtained at different times t, and so we bring it back to time 0 and this gives me a c t into b raised to t. So, this is some discount factor. So, for example, b beta, so this beta could be say 1 over 1 plus r. So, accordingly, when we consider u1 of c t, then we have to discount it back to the initial time, and this is from t equal to 0 to capital T. all right. So, this is the sum of all the discounted utility of consumption, and this is the utility of the final consumption. There are other ways of course, expressing this mathematically. So, the objective is the maximization of this term as well as maximization of this term. Now, remember that these are random variables. So, x of t is going to be a random variable, and so is c of t. So, accordingly, the maximization will involve the maximization of the expected value of these functions consisting of the utility of consumption and the utility of the final wealth level. So, here u1 and u2, these are two utility functions, as I have already explained, and this beta strictly lying between 0 and 1 is some sort of a discount factor. Okay, so now let us move on to utility maximization. So, how you are going to execute the objective function that we have listed above. So, that means how are you going to actually solve this problem here. So, so let us look at the broader topic of now utility maximization in discrete time. So, let us begin with an illustrative example on the potential benefits of portfolio positions being rebalanced over time, and in accordance with that we consider two alternative investments. So, the first alternative is that invest money at 0% interest rate. So, of course, we do not have 0% interest rate in practice, but this is just to drive home the point that one could benefit from portfolio positions being rebalanced over time. So, utility maximization eventually will boil down in the discrete time setup to rebalancing your portfolio from time to time. And what you really need to look at is you have to look at that how to accomplish this rebalancing from time to time, say t equal to 0, t equal to 1 all the way to t equal to capital T. So, that eventually the end result is that you have achieved the maximal possible expected utility of the consumption as well as the wealth process. Okay, so, coming back to this example, so the first alternative is invest money at 0%, and the second alternative is that you invest in an opportunity to double or half the money in each time period, all right. So, this is just like the binomial model, either you can go up by a factor of 2 or you can come by a factor of half with equal probabilities, that is half and half. Okay, so now when you are talking about utility maximization, obviously we have to specify what is the utility function. So, accordingly we consider the log utility. So, let us then consider the log returns. So, that means the utility at the final time point will be log of x of capital T. Then what happens in the first case? So, for opportunity 1, that is this opportunity, the average return on a single unit of currency is, what is this going to be? You have invested, so you invest an amount of 1, since the interest rate is 0%. So, you end up with an amount of 1. So, in that case the final wealth level is 1 and the log of that is going to be of the final wealth level is going to be 1, and this expected value is simply going to be 0, because log of 1 is equal to 0. Okay, now let us look at what happens in for opportunity 2. So, in case of opportunity 2, if we invest a single unit of currency, then what is going to happen? Then either the wealth becomes 2 or the wealth level becomes half. So, its utility is going to be log of 2 and log of half, and it has the probability of half. So, when you are trying to calculate the expectation, you get half here into log of 2 and half into log of half. So, then we can say that the expected rate of return is this expression, and this is nothing but 0.5 of log 1, which is 0. So, so you see that, so this takes care of the second alternative. Now, you see that if you individually invest either in opportunity 1, then the expected return or the average return is going to be 0. If you individually invest just in opportunity 2, then again the expected return is going to be equal to 0. So, however, now we need to start looking at other alternatives. So, remember that in the first case, so if we need to start now looking at portfolios comprising of opportunity 1 and 2. So, the two cases that you have considered, in the first case the weight for the first investment was 1 and the weight for the second investment was 0, and in the second case the weight for the first investment is 0 and the weight for the second investment is 1. So, what we are going to do now is consider another situation where these two extreme cases of complete investment in either of the opportunities is discarded, and we now look at a possibility of taking a combination of investment in both of them. So, that means we take W1 and W2, both of them to be equal to non-zero. So, however, let us see that if we invest 60%, that is weight is 0.6 of the amount in opportunity 1, that means investing at 0% rate, and 40% of the amount in opportunity 2, then the expected rate of return is the following. So, if you invest an amount of 60% in opportunity 1, that means you get 0.6 unit of the currency. So, what you will get is that from opportunity 1 you will end up getting 0.6. Now, the remaining 40% means that you have invested an amount of 0.4 in the opportunity 2. So, that 0.4 will grow either to 0.8 with probability half, or it will come down to 0.2 with probability half. So, that means that for this you will have 0.6 plus 0.8 is the final amount, 0.6 coming from opportunity 1 and 0.8 from opportunity 2, or you will get 0.6 from opportunity 1 plus 0.2 from opportunity 2. So, these two are the possible final wealth level. So, the utility of each of them are going to be log of 0.6 plus 0.8 or log of 0.6 plus 0.2, and then you want to calculate the expected return. So, this return can happen with a probability of half. So, I multiply this with 0.5, and this can also happen with probability half. So, I multiply this with 0.5 and add them up. and this turns out to be equal to 0.057. So, therefore, an investment of 1 unit of currency gives e raised to 0.057 equal to 1.058 units of the currency. That is, you are able to achieve, looking at this 0.058, this term 0.058. So, that means you have been able to achieve 5.8% return per period. So, motivated by this example, we set the goal to determine the optimal proportion of wealth to be invested in available assets for each trading period. So, in particular, the example is consistent with the typical financial advisory of investment in both risky and risk-free assets. Let me elaborate a little bit more on what I am trying to convey here in terms of this motivation. What I am saying here is that initially you looked at two opportunities, and in the first opportunity you had 0% interest, and in the second opportunity you had a likelihood of going up by a factor of 2 or coming down by a factor of half with equal probabilities. And you observe that in both the scenarios, if you just invest completely in those opportunities exclusively, then you end up with getting an expected return to be equal to 0. However, we chose a particular case of a combination of investment with 60% in opportunity 1 and 40% in opportunity 2, which ended up giving you a positive expected rate of return. So, if you run this kind of portfolio reshuffling, just not in the 60-40% proportion, but all possible combination, that is, you look at all the opportunities set, and then you can get a large class of expected utilities values, and your goal is to find out that combination of weights W1 and W2 that is going to give you the largest possible expected utility out of this investment strategy. And this example is just to illustrate one case how you can achieve a greater amount of return by investing in a diversified manner rather than investing exclusively in individual assets. And we start off this as the beginning point of our discussion on how actually we determine what those optimal weights W1 and W2 are in the context of dynamic programming. Okay, so what you do is, so accordingly we begin the deliberation for a single period model, and then we will extend this to the multi-period model, where we will make use of the Bellman's dynamic programming principle. Okay, so we begin with the setup for this and consider a single period model for the market with n risky securities and a bond with the prices being S1, S2 all the way to Sn for the risky securities and B for the bond respectively. Suppose that the investor starts off with an amount x and chooses a portfolio delta vector. Remember, the delta vector comprises of delta naught, delta 1 all the way to delta n to maximize the expected utility of the wealth at time t equal to 1. Right. So, we are taking time t equal to 1 from time t equal to 0 because as you have said, this is for the single period model. So, mathematically what is this going to be written as? So, in concrete mathematical terms, this means that you are trying to find the supremum or the maximum to determine what is the best delta such that you achieve the maximization. So, figure out what is going to be your delta, so that the expected utility at time 1 is going to be maximized or you obtain the supremum. So, this maximization is performed over the vector delta subject to the constraint of the self financing condition. What is the self financing condition? See, you start off with an amount of x and you invest in delta naught stocks, delta naught bonds whose present price is B0 plus delta 1 units of stock S1 all the way to delta n units of stock Sn. And this total investment must exclusively be funded by the exact amount that you have in hand, that is your amount of x. So, just recall that. So, in this context what I want is that we need to recall that when we are discussing this wealth process earlier in a single step model. So, we had x1 is equal to delta naught b1 plus delta 1 s1 of 1. So, this is basically exactly the same expression except at time 1 plus delta n sn of 1, and this can be now rewritten. So, I am introducing this compact formulation of delta I si of 1 I equal to 0 to n, and this is done with just one change, and that is with S naught being defined as B. So, this is for notational brevity. So, the optimization problem subject to the budget constraint is solved using the method of Lagrange multipliers that you have already encountered when you looked at a multi-asset portfolio optimization in the mean variance framework. So, accordingly, we define the Lagrangian Remember, what do you want to maximize? You want to maximize the expected utility of x1. So, what is x1? x1 is nothing but this expression. So, it is the maximum utility of summation delta I s I of 1 I is equal to 0 to n. So, this is the utility of the final wealth level, and you want to maximize the expected utility, and this is subject to your self financing constraint. So, this can then be, this is minus lambda into summation of your self finance. So, summation delta I is equal to 0 to n of S I of 0 minus x. And so, I define this to be my Lagrangian L. So, what do you do? So, we basically want to do the optimization with respect to delta. So, accordingly, what we do is, so delta is nothing but a delta naught, delta 1 all the way to a delta n. So, accordingly, in order to determine the optimized delta i's, we start by differentiating L with respect to each delta I and setting the derivative equal to 0. So, we have partial derivative of L with respect to delta I equal to 0, which implies that the expected utility, so this is going to be u prime of x hat of 1 into S I of 1, this is equal to lambda into S I of 0, and this will hold for all I from 0, 1, 2 all the way to capital N. Now, since I equal to 0, 1 to capital N, so this means that this set of equations constitute n plus 1 equations with the newly introduced variable x hat of 1 denoting the optimal terminal wealth. We also take into account the budget constraint, that means this relation being equal to 0, which results in addition to this n plus 1, we have this budget constraint. So, we end up having n plus 2 equations in n plus 2 unknowns. And what are these n plus 2 unknowns? So, these are delta naught, delta 1 all the way to delta n, and of course, lambda. So, here I just want to note that S naught of 0 is equal to B of 0 is equal to 1, and S naught of 1 is equal to B of 1 is equal to 1 plus R. Now, it is not necessary that I should take this to be equal to 1, but for simplicity I have taken, because we are not going to use this 1 value, but rather we will just make use of the fact that S naught of 1 over S naught of 0, this is just going to be equal to 1 plus R. So, so in that sense, of course, you could have taken this to be some constant, and then we could have taken S naught of 1. So, I could have taken S naught of 0 equal to some constant, and I could have taken S naught of 1 to be that constant into 1 plus R. So, we do not lose the generality, because this is the result that we are going to use. So, here R, so this newly introduced R that you have here, R is the single period. Remember, we are just considering the single period model. So, this is the single period risk free rate. Now, going by the above equation, so if you observe carefully here this relation, so from here we obtain the value of lambda. What is the value of lambda? This is going to be the expected value of u prime of x hat of 1 into Si of 1 over Si of 0, dividing both sides by Si of 0. And remember that this is going to be, so Si of 1 over Si of 0, this is 1 plus r. So, that is what I was referring to, as we will just make use of the ratio, into u prime of x hat of 1 into 1 plus r. So, now that we have obtained lambda, so we can then obtain by substitution that Si of 0, this is going to be E. So, what we do is that we substitute the value of lambda again in this expression and get the lambda in the denominator here to obtain Si of 0. So, this becomes expected value of u prime of x hat of 1 into Si of 1 over E of u prime x hat of 1 into 1 plus r, and this is 1 over 1 plus r into E of u prime of x hat of 1 into Si of 1. So, the numerator remains the same, and the denominator I have taken the 1 plus r out, which leaves me with expected utility of expected value of u prime of x hat of 1. And this is an expression for the price of a risky asset. So, price, I mean the price at time t equal to 0 of a risky asset Si. Okay, so just one last observation is that a variation of the single period model which allows for consumption C of 0 at time t equal to 0 results in the problem a supremum over delta of u1 of C0. Now, this is the deterministic quantity plus the expected value of u2 of x of 1, which is a random variable, with the budget constraint x minus C of 0. Remember that we start off with wealth x, but you can invest only the amount that is left after consuming C0. So, that means x minus C0 can be used to purchase delta naught bonds plus delta 1 units of the first stock all the way to delta n units of the nth stock. So, this should be actually be S1 of 0 and Sn of 0. All right. So, now let us come to an example to illustrate how this maximization of expected utility is accomplished, and for this purpose we again make use of the log utility. So, for this we consider the framework of the binomial model, but we are still we have the single period setup. With the stock, so we have again we have time t equal to 0 and time t equal to 1. So, with the stock price as 0 going, so this stock price as 0 at time t is equal to 0 going up to S 0 into u with probability p, or going down to S0 into D with probability q, which obviously is 1 minus p, and these values can happen at time t is equal to 1. Now, note that we have the restriction that d must be less than 1 plus r less than u. Okay, so now once we have this setup for the asset prices, so we assume the log utility, that is u of x of t is log of x of t, and we denote the investment in one stock. So, we actually not denote, but rather make the investment in one stock and one bond. So, this is a very simple example wherein I am considering the investment in one bond as the general market model, but instead of investing in a capital N number of stocks, we just invest in one stock. And then let us see how the optimization problem in this case pans out. So, we have made an investment in one stock and one bond. So, accordingly I will use the notation. So, that means I have here I have delta naught and delta 1, but what I am going to do that, since we just have delta naught and delta 1. So, I will let delta denote the number of stocks. Okay, so, as a consequence of this, what happens? We observe that if you buy delta number of stocks, so then the total amount invested in delta stocks is delta into S0, and remember that we had an initial amount of x, and out of which we have invested delta S naught in the stocks. So, as a result, the remaining amount invested in bond is x minus delta into S naught. Okay. So, now at time t equal to 1, what happens? So, according to the binomial model, at time t equal to 1, S1 can take two values. Either it can take the value S naught into u with probability p, or it takes the value S naught into d with probability q. So, then what happens? Then what are the possible values of x1? See, your investment in bond, what was your investment in bond? So, the investment in bond was x minus delta into S naught. So, irrespective of whether the stock goes up or down, your valuation of the bond is going to be delta into S naught, or the amount of money that you can get, into 1 plus r, and in both the cases it is going to be x minus delta into S naught into 1 plus r. However, the valuation of your stock can either be delta into S naught u in this case, or delta into S naught d in this case. So, that means your total wealth will be the sum of these two, with the first scenario having the probability p, and the second scenario it has the probability q. Alright. So, now you have this random variable x taking two possible values, the one here with probability p, or the one here which is the probability q. So, next we need to calculate the expected utility of terminal wealth. So, that means it is going to be expected value of log of x of 1. Now, log of x of 1 can take two values. What are those two values? It is going to be either log of delta S0 u plus x minus delta S0 into 1 plus r, or it is going to be log of delta S0 d plus x minus delta S0 into 1 plus r, that is here. And since I am calculating the expectation of the random log of this quantity, so I have to multiply it with the associated probabilities, that is p into log of this quantity plus q into log of the second quantity. So I am just going to do a bit of a reshuffling of the terms in both the cases. So this becomes p into log, so I will take all the delta S naught terms, so it is going to be log of delta S naught into u minus 1 plus r, and plus the remaining term is x into 1 plus r plus q into log, again I combine the delta S naught terms here. So, this is going to be delta S0 into d minus 1 plus r plus the remaining term x into 1 plus r. Now, observe that since the budget constraint has already been accounted for, and how is it been accounted for? Because we have already taken this x minus delta S naught term here. So, therefore, we no longer need to use the method. Now, with the constraint gone, so we no longer need to use the method of Lagrange multipliers. So, differentiating, so this essentially reduces to a single variable calculus problem. So, differentiating the expected value, so we have this expected value here. So, we differentiate this expected value here. Remember that here p and q are given to you, you know what is u, d and 1 plus r, and of course, you know what is x and S0. So, the only factor that you need to determine is going to be the delta, and you need that delta for which this expected utility is maximized. So, essentially it boils down to then maximizing this function here as a function of delta. So, accordingly we differentiate the expected value with respect to delta, because that is what we are trying to optimize, and setting equal to 0 we obtain. So, after some simplification you get delta hat, we obtain delta hat given by the expression delta hat. So, I obtain the delta hat and multiply by S naught and divided by x, and there are a couple of reasons why I am doing this, which I will explain, and this turns out to be 1 plus r into u p plus d q minus 1 plus r closed over 1 plus r minus d into u minus 1 plus r. So, observe here that the term on the right hand side 1 plus r these are known, u and d are known, and so are p and q. So, this is essentially independent of x. Now, also observe carefully that if delta hat is the optimal value of delta, so the delta hat S naught is the investment in stock, and then x is the initial wealth. So, this fraction is going to be just the weight of the investment in the stock. So, accordingly, so I will define that. So, I will define this delta hat S naught S0 as a new variable which I will call pi hat, and this will denote the optimal proportion of wealth invested in the stock, or what is known as the portfolio weight. And you see that this is independent of the initial wealth level. And another form for pi hat is pi hat is equal to 1 plus r, and I have a minus 1 plus r here, into expected value of S1 over S0 divided by 1 plus r minus d into u minus 1 plus r. And the last observation is that, note that pi hat, that is the optimal portfolio weight, pi hat does not depend on initial wealth level x. Okay, so this brings us to the end of this lecture. Just to do a brief recap, what we did today is that we started looking more specifically into the problem of maximizing the expected utility, and for that purpose we started off talking about what is going to be the expected utility of the terminal wealth in case of a single period model. Say we have time t equal to 0 at time t equal to 1, and we explained the general principle of that, and finally we illustrated this through an example where we had the utility function to be the log utility, and we calculated the expected utility of the wealth at the final time point, that is t is equal to 1, in order to determine what is going to be our optimal number of stocks that we need to purchase, that which we denoted by delta hat, in order to achieve our goal of maximization of the expected utility of the wealth at the final time point. So, in the next class we will continue this discussion, and we will move on to from the single period setup to the multi period setup, and we will look at an example of how this can actually be accomplished in case of specified utility functions. Thank you for watching.